Hello, everyone. So let's start. So first off, our first lecture is about inverters. No? So we'll be discussing the properties of the BJT as a switch and the operating regions that we use when we use the BJT as a switch, namely cutoff and saturation. We're going to discuss its use as an ideal, uh, the ideal inverter, no, as the most basic logic gate, and then the use of the BJT in an inverter. No. Then we'll also discuss more realistic VTCs and the definition of noise margins, which we use to define what gates actually, how good gates actually are. So, first off, for an ideal switch, we know that it behaves like this. No? So, for example, when a switch is open, the circuit current or the current across the switch is zero. No? So, there's no current that can pass through the switch. On the other hand, there is any voltage, no, any voltage can appear across the switch, no? So for example, here, Vs would be equal to the source voltage, no? For a closed switch naman, the Is depends on the connected circuit, while Vs is guaranteed to be zero because the switch is uh, closed, no? So, Is, in this case, we know that this would become V over R, no? So, this just illustrates that these 2 points, no? For an open switch, Is is zero, and Vs depends on the connected circuit, or it can be anything, no? In a closed switch, Is is the one that can be anything, and Vs is the one that is zero, okay? Now, when we use the BJT as a switch, no, we force it to be either in cutoff or saturation. No? So this one is cutoff, this is saturation. No? So when VBE is zero, IB and IC are both guaranteed to be practically zero, and we can essentially treat the CE junction as an open switch. That is, no current can pass through it, which is the same definition. No? Then if VBE is high, no, then the switch closes because we can allow any IB or IC to pass through. Now we know that practically the BJT doesn't allow any IC to pass through, pero because of these rules, no, we can practically say that the switch is closed, no, if we are using a BJT. So you can think of the BJT as a voltage controlled switch. Okay? So, when we use the BJT as a switch, no, let's apply it to the resistor network that we used kanina, no? So when VBE is zero, then we are guaranteed that IB is zero and IC is zero because the BJT doesn't have a base current or a collector current. So what happens? Since there's no current, no, the voltage up here, which is V, just put ground down here, would transfer over here without any voltage drop. And so we have the same, practically the same behavior as the one earlier, where we had the voltage appear across the switch. No? And then for a BJT switch with VBE high, we have that IC, no, is allowed to be anything. So practically, if VCE is close to zero, no, then the current across the switch is about V over R, assuming that VCE is zero. No, practically it's not, pero for the operations of a BJT as a switch, this is good enough. No, so for us to be able to use the BJT as a switch, we need to ensure that we are in saturation or cutoff, no? Which means that we need to enforce these conditions. So for example, we want the VBE to be in the saturation voltage, no? Which is about 0.7 to 0.8 in a silicon BJT. No, this is in contrast with the typical VBE on or VBE active voltage, which is 0.6 to 0.7. No? And we also define VBE cut in to be a voltage wherein the VBE starts to turn on the BJT. And we also have VCE SAT, no, which is about 0.2 to 0.3. Okay. So we have to satisfy two conditions when using the BJT as a switch. So we have to ensure that it is saturated. And the most important condition for this is that the ID has to be greater than IC over beta. No? When we're using the switch as an open switch, no? When we're using the BJT as an open switch, we have to make sure that the VBE is less than VBE cut in. No? So that's this one. We need to make sure that it's less than this one. Okay? So, for the first example, if RC equals 1 kilo ohm, is the transistor saturated, no? So here, we intend the VJT to be used as a switch, which is actually a very common use case. So if RC equals 1 kilo ohm, is the transistor saturated? We assume that VCE sat is 0 volts, and we find that IC max would be equal to 10 minus 0 divided by RC, which is about 10 milliamps. All right? So then we find that the minimum beta, no? So we found that IC equals 10 milliamps. We find that the minimum beta at this IC from the datasheet is about 100. So then that gives us an ID that should correspond to this if we were in forward active, no? So this is if forward active. But we don't want to be in forward active. We want it to be in saturation. And the definition of saturation is that the beta is greater than, the base current is greater than what it should be if we were in forward active. So then IB has to be greater than this IB min. And since the IB is practically 0.2 milliamps, it is given here, then we are sure that the transistor is saturated. So for our next example, we have RC equals to 20 ohms, and we're asking if the transistor is saturated. Same process as earlier. We have 10 minus 0 divided by 220 would be about 50 milliamps. No? And then we ask ourselves, okay, what would be the corresponding IB if we were in forward active? Then it turns out to be 0.75 milliamps because at 50 milliamps, the beta is 60. Okay? So then we find that 0.75 is actually above the IB, 0.75 is actually above the current IB, which means we are not in saturation. Okay? So, an interesting observation about using the BJT as a switch is the fact that we favor actually saturation and cutoff because of another reason, no? So aside from VCE being very close to zero, no, practically close to zero, which is ideal for a switch, no, in saturation, you actually get a much lower power. So for example, here, the power is practically zero at the point wherein we are in saturation. Note, for the 1000 ohm case, this is the same as the one earlier, no? We have a very shallow slope for the load line, which corresponds to this point in saturation. And for the 220 ohm case, we are deep in forward active, which is over here. No? So if we compute the power for each of those, the one in forward active would be consuming nearly 1 milliamp, while the one in saturation would be consuming nearly zero. It's practically zero, but it's somewhere close, somewhere non-zero. No? Which is another reason why we would typically favor saturation over forward active. So finally, we introduce the inverter, no, which is something that we use the BJT as a switch for. So the inverter as a logic element has this behavior. If you put in a 0, you get a 1. If you put in a 1, you get a 0. But practically in the real world, there is no actual 1 and 0. What we have is a high voltage and a low voltage. So then, if we put in a high voltage and a low voltage, we're supposed to get a low voltage and a high voltage, respectively, if we treat the inverter as a circuit element. No? An important property of the inverter would be the voltage transfer curve as shown here. So if we try to implement an inverter using a transistor, we would have something like this case, no? So For example, here, an inverter operating with power supplies at V plus and 0 volts can be implemented using a switch with a resistive load. So any switch can work. You can use a MOSFET, you can use a BJT. So then our actual basic CE amplifier can be used as an inverter if we bias it for saturation. So when we're trying to use the BJT as an inverter, no? Let's say, for example, that Vin was high, no? Higher than, say, 0.8, no? Which is VB sat. So if it's higher than 0.8, then the BJT would turn saturated, no? So then V out would be equal to 0.2. So then when V in is high, actually, the BJT gets saturated and V out is nearly zero, no? This corresponds to the BJT switch being closed, which means this is an inverter. V in high turns out to be V out low, no? On the other hand, when V in is low, something like zero, no? Then VBE sat won't be reached because this would also be 0 volts. So then V in low causes the BJT to be cut off. What happens in cutoff? There is no IC, there is no IB. So when there's no IC, then VCC just shorts to V out. So then V out is high, no? And this basic CE circuit, no, then becomes the inverter that we've always talked about, no? So, for example, let's try to build an inverter with a 2N2222, no? Whose minimum guaranteed beta is 100, no? So then first, the rule is we want to stay in saturation, right? So then we think, okay, what causes saturation? Well, saturation happens when the IB is actually greater than the allowable IB by IC over beta. So then let's compute for IC. If this is in saturation, no, that is, if this is practically zero, then, or 0.2, no, which is VCE sat, then VCC minus VCE sat over RL would be IC, no? So that calculation turns out to be 24. Now, IB has to be greater than this 24 over the beta that it corresponds to. If beta minimum is 100, then we get that IB has to be greater than 0.24 milliamps. So then we know that IB, no, has to be greater than 0.24 milliamps. But what is IB? Well, IB can be found because V in has been given to us. That's 3.3. And if we're in saturation, then VB is at, should be here, no? VB is at should be here. So then V in minus VB is at divided by RB should be greater than 0.24 milliamps. No? Rearranging the equations, we find the proper constraint for RB. No, RB has to be less than 10.416 kilo ohms. No? So then, okay, if RB, so the constraint is that RB has to be less than something like 10.5 kilo ohms, no? So then, if it's a one-sided constraint, why not just let RB equals 0 and make it easier for us? Well, remember, if we reduce the resistors values, no, the problem is the current might increase, and it does here, right? As RB decreases, IB increases because they're inversely proportional in this circuit. So then the power becomes, the power at the BE junction becomes IB times VB isat, which is 0.8 times IB, no? So then the problem is that the power might exceed the allowable power of the 2N222 BE junction. No? So then we have to check that before we decide on RB. So then RB, that will set a constraint that RB has to be greater than some minimum. No? So, in a sense, no, okay, that's the example of a real inverter. No? Pero in general, the voltage transfer curve of real inverters do not have such nice slopes. No, we know that the voltage transfer curve of a CE amplifier, we know how that looks like, and it kind of looks like this, right? So this introduces a constraint that is, since this voltage transfer curve is soft, how then do we define where is 0, where is 1? Where does 0 start, where does 1 start? And this is where the concept of VIH, VIL, VOL, and VOH appear. So we define these quantities at the points where the slope of the voltage transfer curve becomes -1, as in exactly -1, but this is an arbitrary decision. So what does that help us do? So at the -1 slope, we define that the input voltage that is considered low, so below this is considered 0, no? And above this is considered 1. And then for this one, below VOL, rather, this is the output voltage that is considered 0. And above VOH, this is the output voltage that's considered 1. No? And you can see that in most voltage transfer curves, if you put VOH, VIL, VIH, and VOL, no, in the same y-axis together, VIH and VIL will always end up between VOH and VOL, no? And the practical reason for this is this, no? If you have two gates cascading against each other, no? Then if one happens to happens to have an input of the minimum possible, right? Something like VIH, no? In this curve, you basically gave it this voltage, no? And this would correspond to at least a V out low, no? And so, this V out low is well within a margin of something that's considered low for the next inverter. So then the next inverter will be very squarely in the output high region, no? So remember I mentioned margin, no? So then we introduce the concept of noise margins here, no? That is, if you have an inverter, no, that's outputting VIH, for example, that's outputting VOH, for example, how much noise can you tolerate in between the inverters such that it won't actually exceed or rather go under something that's considered still 1, no? Because after VIH or below VIH, you don't know what this is anymore, no? And this is why we need these noise margins, okay? So for this next example, let's try to see where the noise margins are for the practical CE amplifier, or where the VIH, VIL, VOH, and VOL are, no, in the basic CE amplifier. So for example, here, VIH is typically found in the border between active and saturation. The reason for this is this. The active, no, has a gain, no? So this has a gain of greater than 1, of course, no? And in saturation, the gain quickly goes below 1. So practically, no, it should be reasonable to assume that slope equals -1, no? This is magnitude, by the way. Slope equals -1 should appear right at the border between active and saturation. No? Same for the border between cutoff and active. This thing has a slope of 0, right? And this thing has a slope of greater than 1. So the transition has to be here. So then we consider this VIH, we consider this VIL, no? And we consider this VOH, and we consider this VOL. Okay? So then for us, no, we consider that logic 1 is somewhere between 1.24 to 3, no? This evaluates 1.24. And logic 0 is considered somewhere between 0.0 to 0.5, no? This is yung input natin. Okay? So with that, ends the first lecture.